Welcome back. My name is Hiraku Murakami. I'm here with NovaEdge Academics, and today we'll be going over topic A2, forces and momentum in IB physics. We're going to first start off with force overview. I'm sure you already know what a force is, but recall that force is a vector, and it's a vector quantity, and it has a magnitude and a direction. The importance with this is that when dealing with vectors, you can add or subtract them and to find the net value. In this case, it is the net force. And the importance of the net force is that it tells us where the object is accelerating. And that's given by net force is equal to mass times acceleration. We'll get there in a second, but I want to re-emphasize the point about how you can add or subtract. So as an example, if I had a box and there were two people on each side, one was pushing it with 50 newtons and the other was pushing it at 100 newtons, then I can easily tell that the object will be traveling to the left side because there is a net force of 50 newtons to the left, right? It's quite simple, right? Now, another really important thing about this arrows that we draw is that the length of the arrow is supposed to be proportional to the magnitude of the force. Now, the importance behind this is that even without knowing the value, I can actually determine which direction it's traveling in. So as an example, if I have an imaginary ball and one person is pushing it this way and another is pushing it this way, how do I determine which way the object is accelerating? Well, I can connect the two arrows and see where the force ends up. So for example, if I move this arrow to the tip of the other arrow and connect from the beginning to the end and draw a red arrow, that is actually the net force. And that net force tells me where the object is accelerating. I can do this with multiple arrows as well, which becomes really important. So as an example, if I have a ball, one is going this way, another is going this way, another is going this way, and another is going, let's say, this way. Okay? What I can do is combine these arrows and see where the net force is going. So let's do that. Connecting from the initial point to the final point, I get that this is a net force. So if I add all of these forces up, that is the direction of the object. So really important key stuff here. You can just connect the arrows and see where it's going. Another thing about this net force is that we can mathematically calculate it using mass and acceleration. So this is mass and this is acceleration. Remember that this is in kilogram meters per second squared. So the SI unit of force is kilogram meters per second squared, which is actually equal to what we call a Newton. Okay, so this is how we calculate the net force. Important distinction is it is the net force. It is a sum of all the forces, sum of all the force components. Why is this important? Well, because in your classroom you might hear that force is equal to ma. This is not true, or this is not entirely true. It is the net force that is equal to ma. Okay, there's a clear distinction. Let's talk about the first force. So the first force we'll learn is the weight force, and the weight force is due to gravity by a certain planet. In our case, it is by Earth. So force of gravity or weight force is given by mass times by the gravitational acceleration. So this is in kilograms meters per second squared. Now, on Earth, we have that g is equal to negative 9.81, but on the moon, it could be negative 3, or on other planets, it could be different, and it depends on the mass of the planet and the size of the planet, right? We'll be covering this more in topic D in detail, so stay tuned for those videos, but for now, we're going to cover just Earth. So if we use that calculation, we can do number 1. So pause the video and try this. So the answer to A is 12,500 Newton. The answer to B is 32.40 Newton. Be careful about the unit. It is given in grams, which means that this is 3.240 kilogram. Note that I only use 10 instead of 9.81 for simplicity. If you want the actual value, just multiply by 9.81 instead. Number 3. To do part 3, I'm going to write 445 is equal to 50 times by g, right? So g is going to be equal to 445 divided by 50, which is 8.9 meters per second squared. Now, one thing to keep in mind is that the weight force is always directly straight down towards the source of gravity. In this case, for our Earth's sake, it is towards the center of the Earth. Okay? Now let's do normal force. Okay? So imagine if there's a book on a table. Okay? Well, the book has its own weight, right? That it's bringing it down, and that weight is equal to mg, right? However, the book is not accelerating, right? If it is not accelerating downwards, that means that there is no net force. The net force is not downwards, it is 0, right? So if the net force is equal to 0, that means there has to be a force that's going up that's canceling it out with the same magnitude. This is what we call the normal force. So the normal force is a reaction force. It comes because there is a weight force that's being pushed onto the table. So the table will push it back with a normal force that's equal to the weight force in this scenario. Now the normal force, always keep in mind that it is always perpendicular to the surface. Okay? Always perpendicular. So as an example, if I had an object that is sliding down this ramp, let's say this is 50 kilograms, right? First, let's draw the free body diagram. What does a free body diagram mean? We just draw the forces that is at play. For example, in this case, we have the weight force always going straight down, right? We also have the normal force. But remember, normal force is always perpendicular, right? So perpendicular to the surface means this way, okay? Now, for the normal force, there isn't really a formula we can just plug in like mg, right? So we have to evaluate the weight force first, okay? Well, first, can you tell me which way is the object accelerating? Well, it's definitely accelerating downwards, right? So if it is accelerating downwards, we actually need to split the axis into two first. Before we did y and x in projectile motion as well. If you want to learn about projectile motion, check our other video. For us right now, we need to divide it in this direction. And the reason why is because net force is on this axis. Okay, if the net force is going downwards, then you would probably want to split it downwards to y and x. Now for now, let's do this. Let's say the ramp is equal to 30 degrees in angle. Okay, so my question to you is, can you figure out the acceleration of the object in this direction? Okay, so we want to find A. How do we do that? Well, first, I'm going to split the weight component in the red axis. So if I were to split the weight component, this is what we get. We use a vector addition, right? This vector plus this vector is equal to this. This is what we just covered, right? So this component here is actually w cosine 30 degrees. This here is w sine 30 degrees, right? Trigonometrically speaking. So now I want you to ask yourself, is the object accelerating in this axis? The answer is no, which means that there is no net force. That means that r is equal to w cosine 30 degrees. These two forces have to cancel each other out because there is no net force in that direction. If I were to calculate this, I get 500 times cosine 30, which is equal to 433 newtons. Okay. Now the net force is what remains, and that is this guy, right? Because these two canceled out, so this is the only thing that's left. So the net force is equal to w sine 30, which is equal to 250 newtons. Okay. Now, because now we know the net force, I can find the acceleration of the object. The net force is equal to ma, which is equal to 250 newtons. So if I divide both sides by the mass, which is just dividing by 50, I get that acceleration is equal to 5 meters per second squared. Okay. Now let's talk about tension. Tension is another type of reaction force, similar to the normal force. Imagine if I'm hanging a block from the ceiling, right? There's a rope that's hanging the block from the ceiling. There's going to be a weight force that's going down, right? But we know that the net force is 0 because the block is not moving. It is stationary. It is at an equilibrium, right? That means there has to be some force that's holding it up the same way there was a normal force. This is what we call the tension force in this case. It's very simple, very similar to what we did. So let's do a little bit complex problem. Okay, so for example, if the weight here is 900 newtons, we can easily say that the the tension is 900 newtons because it is equal and holding it up. Let's do a more complex problem. So pause the video and try this on your own. Now, if I wanted to solve this, I need to split this into two axes, and it's already split into y and x. So let's do sx, sy, tx, and ty. Okay, this makes it really simple because now I can compare these three that are on the same axis, and I can compare these two that are on the same axis. Now we know that the net force is equal to 0 in all directions. So the net force to the right and left is 0, net force up and down is 0, which means that Tx has to be equal to Sx, right? Very important. So here I know that this is 50 degrees and 30 degrees. So this means that T cosine 30 is equal to S cosine 50. I'm just going to isolate and do this. So now we have an expression of T in terms of S. This becomes important in the next section. So let's do the y-axis now. In the y-axis, I know that Ty plus Sy is equal to the weight force. So Ty plus Sy is equal to the weight force. That is, T sine 30 plus S sine 50 is equal to 98.0. This is 98.0, right? So now I can actually use the previous expression to solve for this problem. So I'm going to plug in T into here. So that is S cosine 50 over cosine 30 times it by sine 30 plus S sine 50 is equal to 98.0 Newton, right? Because here that's equal to T. We already established this before. Excuse me. So if I factor out S, I'm going to get the following expression. And let me just combine these two with tan. So that is tan 30 right? So I can solve for S now. So S, if I divide both sides by this guy, then I can solve for S. So S is going to be 98 divided by cosine 50 tan 30 plus by sine 50 that's going to be equal to 86. That's going to be equal to 86.2 Newton. Okay, so I can find S is equal to 86.2 Newtons. Now I can find out T because I already have an expression for T. So T is going to be 86.2 times it by cosine 50 divided by cosine 30. This is from here, right? So that's going to be equal to 63.96, which is 64.0 Newton in a correct significant figure. I'll cover in a separate video what significant figures are, but for now that is 64 Newtons. Let's do the next one, elastic force. If I were to pull a spring or a elastic band, I need to put a certain force. We can mathematically calculate this using this formula, where K is a spring constant. And X is a displacement, or how much I stretched it. Okay. Now you might encounter this graph where it plots force time to the extension. Just know that the slope is K because if I divide both sides by delta X, then I get that K is equal to F over X. Okay. Now let's do friction. Now friction exists all over in the universe, right? If I try to slide an object on a surface, I experience something called friction. It is the resistive force. And there's an expression, a mathematical expression to calculate this. And that is mu times R. Now, mu here is the drag coefficient. Okay, and this is from 0 to 1. Okay, now R is something we already did, which is the reaction force. Okay, so as an example, if I wanted to drag a box along this line, and there's a reaction force that's equal to the weight, so let's say 90 newtons. If the surface roughness, right, if the surface is really rough and it has a drag coefficient of 0.3, then I can calculate the force of friction equal to 0.3 times it by R, which is 90. That's going to give me 27 newtons. Okay, quite simple. I can also include this in this problem set that we did. I just said that the net force is equal to W sine 30, right? But what if there's a friction force? What if there's a friction force going this way? Because remember, friction force is a resistive force. It will always go in the opposite direction of the object's travel. So if there's a friction force here, and let's say that mu is equal to 0.3, I can calculate that this is 0.30 times by R. And I already know R is equal to 433. Right? So 433 times by 0.3 is 130 newtons. Okay? So that means the net force is equal to W sine 30 minus by the friction force, which is 130. And that's going to be equal to 250 minus by 130, which means it's 120 newtons. Now, if I wanted to find the new acceleration, I would divide this by 50 kilograms. That's going to be equal to 2.4 meters per second squared. Okay, due to friction, the acceleration becomes slower. Okay. The next is viscosity, and viscosity is a measure of how thick the liquid is, right? So because we just talked about friction, now I'm going to talk about drag. And drag is a term used more for fluid, right? When the tennis ball is traveling through the air, it experiences air resistance, which is a form of drag, right? So when the ball is experiencing a drag, we want to be able to calculate that mathematically. And here we have one mathematical model which can approximate it. And that is 6 pi times viscosity times by the radius times by the velocity of the object. Okay, and that gives us the drag of the system. Okay, so being able to measure viscosity is very important. So let's say honey is very viscous because it is very thick, which we can expect there to be a larger drag force. Okay, now let's talk about buoyancy force. The buoyancy force is a force of floating, right? We know that less dense materials can float on water. For example, oil floats on water, right? So as an example, we have a ship that's floating on water, right? Now, how can we calculate the buoyancy force, right? And there's a specific formula for that, and that is rho times V times G. Now, rho here is the density of liquid. V is the volume of liquid displaced by the object that is floating. So in this case, that is the volume here. That is what we're interested in. Okay, be careful. Some people might just take the entire volume of the ship. That is not correct. We just want the volume submerged because that is the only portion that is experiencing that floating force. And G is just the gravitational acceleration. So let's try this problem and I'll show you how we use this exact equation. So pause the video and give this a try. Okay, so first I want to find out the weight of the block. Now I know the weight of the block is equal to mg, right? But I don't know, they didn't give me the mass of the block, but they did give me the dimensions of the block and the density of the block. So remember that mass is equal to density times by the volume, right? So the density of the block is equal to 880 and the volume of the block is 5 times 10 power of negative 2 to the power of 3, right? So what do we get? We get the 880 times okay, we get this is equal to 0.14641. Okay, multiplying that by G, we get that this weight force is equal to 1.46 Newton. Okay, now the thing is the buoyancy force has to be equal to the weight force because they are at equilibrium, which means that buoyancy force is equal to 1.46. So 1.46 is equal to rho VG. Okay, rho is equal to 1000, V we don't know, and G is 9.81. So what do we get? V is equal to 1.46 times 10 to the power of negative 4 meters cube. Okay? Now, for me to find out the length at which the box is submerged, so if I draw a diagram, it's this portion that I'm interested in, right? Right? So this length that I'm interested in. So I can just divide by the area to find the length. So if I divide this by the area, I get 0.0484, which is meters, which is 4.8 centimeter. And there you go. Okay, let's talk about viscosity as an IA idea, right? A lot of teachers fail to mention some good IA ideas, so here's a really good one. So one IA idea is to measure the viscosity of a liquid. Now, if we have a system like this, where we have a very, very long beaker, right, and I have a metal ball that I know the dimension of, I can measure the radius, I can measure the mass, right, all of that stuff, and I let this go, right? At one point, we're going to reach something called terminal velocity. If you don't know what it is, check the previous video. But remember that at terminal velocity, we actually have net force equals 0. What does that mean? Well, the ball has weight, drag, and buoyancy force all acting at the same time. Well, that means that they cancel each other out, which means W has to be equal to buoyancy plus drag. Okay? So these are the equations that we have. Now, here's the thing. We know mg for measuring it. We know rho vg, right? And we also know 6 pi r and v. So all of these are known, right? Pause the video if it's a bit difficult to follow, but all of these are known. The only thing we don't know is the viscosity. So if we're able to measure the velocity of the ball, we can actually obtain the viscosity of the liquid, right? And this is a great idea, IA idea, because you can say, okay, what is the relationship of the viscosity with temperature, for example, right? If I make the honey higher in temperature, it actually decreases in viscosity. But by how much? Is there a mathematical model to prove this? These are some explorations that you can do in your IA, okay? And we'll be covering a full video on how to write your IA from scratch to the end, so stay tuned for that. Now let's talk, last but not least, about Newton's law. So these are the 3 Newton's laws of motion, and you need to know them by heart. So law number 1 says a body at rest will remain at rest unless it is acted upon by an external force. That sounds quite intuitive and logical, right? Now number 2 says that net force is equal to ma. That is something we already covered. And number 3, for every action, there is an equal and opposite reaction. A lot of students get tricked by this statement. What does that mean? That for every action, there is an equal and opposite reaction. It doesn't make sense, right? Well, I'll give you a few examples. An example is if a skater pushes on a wall, that skater is going to travel to the other direction, right? So what's happening? The skater is pushing on the wall. So first, I want you to think, which way is the force exerted on? The person is pushing the wall, right? So the force is going this way. However, the person is accelerating to the other way. Why? Because the wall exerts the same exact force, but on the opposite direction. Another example is, let's say, push-ups, right? If you do push-ups, and if you really think about it, which way are you pushing? Well, you're actually pushing on the floor, right? Towards the center of the earth. You're pushing downwards. However, your body goes upwards. Why? Because there's an opposite and equal reaction force done by the floor. That's why, if you train your muscle, you can push harder and you can accelerate faster, right? Another thing is pushing off the wall from a swimmer. And another good one is a bird. How does a bird fly? Well, it flies because it's pushing down on air. And all of those air particles, right? All of these air underneath the wing, when you flap the wing downwards, you're pushing the air, and all of the air is exerting the same force backwards, right? That's why with greater area, you can push more air, and more air means more lifting force, okay? So we're gonna stop here. Stay tuned for the next one where we talk about momentum. Hey guys, thanks for watching the video. If you find these really useful, then consider giving us a like and subscribing to our channel. For questions, leave them down below in the comment and we'll try to get back to you. For more academic resources, visit our website at NovaEdgeAcademics.com. We offer one-on-one tutoring service as well as college admission strategy. Let us know what you'd like us to cover next, and we'll see you in the next video.